Hello, everyone. Good morning, good afternoon. Um, Welcome to the September Gen3 Community Forum. Uh, for this month, we decided to do something a little different because the GA4GH plenary is ongoing right now, that we would focus on GA4GH standards in Gen3, how they've influenced Gen3 services, and also how Gen3 team has contributed to them. So just some quick housekeeping items. You're all muted by default, so just stay muted unless you have a question at a question period. Um, I'm Michael Fitzsimons, Director of Research Programs and Scientific Outreach for the Center for Translational Data Science, which is the Gen3 maintainer. Um, and I guess the only other thing is we'll have ample time, I think, for questions after presenters, but feel free to ask questions throughout in the chat. So with that, I'm gonna turn it over to Bob Grossman to set the stage for Gen 3 and GA4GH.
So I want to welcome everyone to the call. Binam and Michael and I are at the GA4GH meeting, and we've had some wonderful interactions with the Gen3 people here, and some extremely fruitful discussions. You'll hear more about those, over the next few months. I'll quickly remind you of what GA4GH. Many of you are quite intimately involved. In the next couple slides, then pass it over to the others for the technical presentation. Next slide. So GA4GH is a standards organization around genomics and health, as you can see from its name, the global lines for genomics and health. We've been involved in GA4GH in sort of two complementary ways as Gen3. One, the Gen3 systems are some of the larger systems that are used around the world to handle genomics and health-related data. And a lot of our work has directly or indirectly led or refined or contributed to some of the standards GA4GH uses. DRS, which you'll hear about, is a way to access data. You'll hear about that today. Our JWT token service and fence was different, but broadly related to what became Visa and passports at GA4GH, and we converged to the Visa and passports. We're in the process of that now. But as you'll hear today, it's helpful as we interoperate with other platforms, and as individual groups on the call set up their own Gen3 to make it easier to interoperate. It's helpful to have some standards. GA4GH is one of those standards. Another group that's active is the Research Data Alliance, RDA. And over the years, I've been concerned sometimes of the lack of alignment of RDA and GA4GH. And I was very happy to see a memorandum of understanding between the two organizations that was announced today, that was announced at this workshop. There's a Research Data Alliance group called the Health Data Commons group. And this is one of the, there are several groups in RDA that do data commons, but the Health Data Commons group seemed as close to what we do here as any of them. I'm going to co-chair the Health Data Commons group with Lauren Maxwell from the University of Heidelberg, and I think there are other co-chairs. This is just starting, but one of my goals is to align what we do in Gen3, both to GA4GH and to the relevant RDA standards when appropriate. I know many of the people on the forum are much more involved in the Health Data Alliance, in the Research Data Alliance than I am, and I welcome your participation in this so that we can align Gen3 with relevant standards. And our goal obviously is when there are great standards or widely accepted like FHIR to sort of support them in Gen3, and when they're not, to make them, such as DRS and some of the others. Next slide. So one of the things I think we could be proud of is they're roughly a 12 to 16 what are called driver projects. These are large scale projects. They're supposed to help set standards and make sure the standards align to real use cases, real requirements. The Biomedical Research Hub, which is a mesh that links together a number of commons, was selected a couple of years ago to be a driver project. We're very proud of that. Most of these driver projects are supported by large national organizations, and this is, if you will, community effort from the people on this call and slightly broader to show that Gen3 Data Commons can individually support standards and collectively support emerging standards such as those we're trying to push to create data meshes and data fabrics from data commons. We all also are an important part of three other of the US driver projects: the Cancer Research Data Commons, Biodata Catalyst, and CPI. And one of the reasons the partnership we have with the different groups in Australia and New Zealand is so important is, we like, Australia and New Zealand play special roles in bridging between US standards, such as some of the standards you see supported by these driver projects on the screen, versus European standards from Elixir and EBL and many of the others. And so, the kind of work that the Australian and New Zealand and other emerging Gen3 Commons can do for standards and alignment is absolutely critical. We're so happy to be working with the groups that we're meeting with this week. Next slide. So I'm going to pass it to others for the rest of the slides.
We're handing off to Michael Lukowski, also from the Center for Translational Data Science at the University of Chicago.
Thank you, Michael. I just want to say it's nice to see everyone, our Australian colleagues that we don't get to see every day in person. So it's nice meeting you and seeing you in person. I'd also like to say my Wi-Fi on in my hotel is pretty bad, so I will not use my video in case that can save some bandwidth. I would usually turn my video on, but I just want to be able to get through these slides. So next slide, Michael. So first off, we're going to talk about the Data Repository Service, or DRS. The DRS standard is pretty narrow, but it's like that for design. The main responsibility of DRS is to host data objects. Gen3 uses the IndexD service, and it conforms to the DRS standard. And I would like to say that, or I'm happy to say that, I'm a co-champion of DRS for GA4GH in the cloud workstream. And Gen3 has been probably the main driver of DRS. We to be it is today, and it's widely used. We have currently 27 petabytes of data in DRS servers, but around the world it seems to be around 40 petabytes of data. So it's a very widely used standard, and it's a great host your data with unique persistent identifiers, so that no matter where you are in the world, no matter where the data moves around in the world, you have a way to link your data back to a single place. Next slide. Yeah, so I added a slide here to show exactly what is going on. I'm sure on everyone's laptop it's kind of small to see, my small font on the right-hand side, but on the left we see what it looks like to get a DIRS request from CRDC. So you go to the CRDC website and you use GA4GH/DIRS/v1/objects, whatever. But the interesting part here is that there is this DG40FC and then a UUID that follows after that. This DG40FC is what we call a prefix, and together with the GUID that follows that, you can get a compact identifier. And so what this allows us to do is to get an identifier that is globally unique. And this prefix DG.40FC is registered on identifiers.org, and that is mirrored to n2t.net, I believe is the other website. So that means that even if you just got this DG.40FC slash and then the rest of the GUID, you could resolve that at identifiers.org at this point back to. This is extremely useful because even in Gen3's lifetime, we have seen cases where the underlying URL for a website changes. So it's just broken. You couldn't have gotten the data back. Thankfully, we have addendum to the standard, this prefix compact identifier tool. So that way, when things do change, if data moves around the world, if data moves anywhere, or your URL changes or whatever, you are able to get this data back. And then on the right is just the output that I like to show. This specific file has many different ways of getting the bytes that are related to the file. You can see that in the access method section of the JSON output, there's an array of Google, HTTPS, and S3. So there's multiple ways to get this data. The also gives you back the checksums and file size, file name, all that sort of file metadata that is necessary to ensure that when you downloaded the file, the data is not corrupted, you have the correct file, and you can be assured that you are working with the correct data. Next slide. Okay, so moving on to more authentication and authorization, we have passports and visas. Passports and visas is a way to sort of bring all of your data into a single spot, or work with your data with a single access token. I would say that in quotes because there's some changes that need to be made to the passport and visa specs, but I'll get into those later. So the main idea of a passport and visa is exactly how you would use your passport for international travel. You, as a researcher, have your passport, and the individual data repositories would be able to grant you a visa that says, hey, you have access to this data. These are called clearinghouses. So a clearinghouse would grant you a visa. What this allows you to do is to grab a bunch of your visas from around the world, all of your data resources, and then you would be able to just bring your passport with you to your analysis platform, let's say, and then bring your data from all over the internet, and you only need to use your passport as a single token that you pass to all of the different resources. The resources would then be able to parse your visas and see, you have my visa, so I can grant you access. The Gen3 platform currently is conforming to NIH RAS. I think in the next few weeks or so, RAS will be turned on in Biodata Catalyst again. But there is a sort of rift between NIH RAS and the GA4GH passport spec. It might not really be a good use of time to talk about these differences, but just know that they are working within the passports and AI work stream to sort of bridge the gap here and create a unified standard so that RAS and passports are talking the same language. Yeah, so next slide. Yeah, I thought it was a good idea to show the GA4GH diagram of how a passport works. So you are a user, you get access granted to you by a platform, and when you sign in, your passport broker can issue visas to you. And as you can see on the right, this data steward and data access request portion of the diagram is also very complicated. GA4GH has ways of sort of dealing with this with duo codes, data use ontologies, and stuff like that. But we don't really use that. Our data access usually comes from something like dbGaP or SRA. But as you can see, the data access committee will add the approval for the visa, and the visa broker and the visa service provider will be able to add visas to your passport. Next slide. Okay, Data Connect is the next one. So Data Connect is a standard for discovery and search, and it mainly describes metadata. As some of you know, Gen3 has a service, the metadata service, or MDS, that basically handles arbitrary metadata for a persistent not a persistent identifier, for any identifier. What this allows us to do is to just, if there is a data object in DIRS or IndexD, that's something that needs a little bit more metadata to describe it, or sometimes we use this for the aggregated metadata service for the BRH to sort of handle information of metadata transfer between multiple data commons. This is how we use this. The Data Connect is a different standard that actually describes tables. I think actually the next slide has this information. Can you go to the next slide, Michael? Yeah. So Data Connect uses a concept of tables. So if you can think of the metadata service having each persistent or each identifier that has metadata associated with it, each object in Data Connect would have its own table associated with it, and each table has its own schema. So that means that our metadata service and the Data Connect are basically describing the same thing. The only difference is how the mechanism in which it describes it. So I'm currently, mocking up the design details that we would need to do to ensure that the metadata service is Data Connect compliant. So that would mean that each object in metadata service would be its own table, and each table would have its own schema that we could make it arbitrary. So what that would mean is you would then be able to search the metadata for a specific object through its table, and you can get the schema back so you can understand it in a programmatic way. Next slide. Yeah, and we'd also like to talk about some future standards that we're going to look through at Gen3. Next slide. Okay, so the first one is PFB. So this isn't a standard yet, but we have developed PFB and mainly for system interoperation, but we feel that there is a sort of lack of this information or lack of a standard in GA4GH. So for quite some time now, we have been sort of scheming as to how do we fit PFB into GA4GH. We're currently looking for a work stream to add this to. Two that come to mind are cloud, which deal with the cloud work stream or cloud information and technologies, and the discovery work stream. The discovery work stream is like Data Connect, like search and sort of metadata information like that. So we are still looking for how to fit this into GA4GH, but we think it's a good addition of a standard to the group. Next slide. Okay, so this is a PR that we made to the DIRS standard. IndexD for many, many years has had a stats endpoint. So if you go to pick your favorite IndexD server and type /stats, It'll give you the total file size and the total object count of all the data that's in a IndexD server. I was showing this off to people in the cloud workstream, and they said, why don't we add this as a PR to the DIR standard? So I added it as a PR. It was merged into the development branch. So the way this works is now this PR and a few others are up for vote currently. So the next release for DIRS will be 1.5. So the way it works is individual contributors will make their PRs. They will go to the cloud workstream where we will talk about them. And if they're deemed to be good and comments are resolved and all that sort of stuff, it will be merged into the development branch. The development branch will then be sort of a reference as we add all the different PRs for a given time. We will then build up enough PRs to then make a release. So currently we're in DIRS 1.4 and we are looking to move to release 1.5 soon. So that means that the PR for DIRS 1.5, like just the release of it, gets sent to all the driver projects and the implementers of the standard. Everyone votes on this release, and you either give a +1, a 0, or a -1. +1 being good, 0 being neutral, and -1 being I have serious concerns with this release. Usually we just look for the +1s and 0s, and as soon as we count them up and it's all okay, we then release the new standard. And if there are any -1s, we usually will have a talk with the driver project. I saw Brian O'Connor is on the call. He's the other API co-lead with me for the DIRS standard. Next slide. Okay, so tax execution service is something we are looking to implement with our Nextflow implementation that is currently being developed in BRH. So what is TESS though? TESS is a standard for defining a schema for describing batch execution tasks. The way you can think about this is a single workflow has many tasks that are going on. I'm not a bioinformatician, so I don't know the actual individual tasks, but each task can be thought of as a batch script that's running something. So TESS is an API that handles all of these individual bash scripts. You submit your job, and then the underlying architecture will execute all the everything it needs to do. It will then give an output, and then the workflow engine, Nextflow, Cromwell, SnakeMake will then take all that data and sort of collate it and understand it as an output of the entire workflow. So the future benefits of TESS are, allowing workflows to be run on Gen3. It gives visibility into what the workflow is actually doing, and it allows Gen3 to offer control and monitoring of workflows. Next slide. And now I'll hand it off to Kyle.
Thanks, Michael. Just briefly before we hand it off to Kyle, I think we have a moment if people have any questions. For Michael or Bob. Okay, we can get to the questions at the end. Then I'll hand it off to Kyle Ellrott. Take it away, Kyle.
Thank you. Yeah. So I wanted to kind of continue with that small introduction that was given on TESS. If you want to go to the next slide. So yeah, the cloud workstream for GA4GH has APIs kind of addressing all of the different layers that are necessary for compute. And basically right below what you consider like run an entire bioinformatics workflow is the necessity just to run an individual task. And so this is, I just mentioned, like more of the command line level execution. How does that occur? Can we go to the next slide? And so this is a simple API. It is designed to be very minimal, but unified. Just to give context for why this was inspired, the time, a lot of people work on HPC environments, and so you're using something like Slurm or Grid Engine to basically dispatch out the jobs. At the same time, AWS had proposed a new standard called AWS Batch. Google had one, which I think was their Cloud Pipeline API. And then more recently, there's an Azure Batch API. Every one of those things do effectively the same work of take a command line, move it out to some random execution machine, compute node to actually do the execution, and then, wait for it to finish, and then package up the results and move them back out. And every one of those is a completely different standard. And so if you want to write a system that does more than one job, if it actually does something like a workflow or even like a grid search or some sort of like large scale programmatic analysis where you're trying to do one of the things we've been thinking about is like machine learning parameter optimization. And I wanted to send out thousands of jobs, view them, and adjust the next set of jobs that you'll be doing intelligently. So how do you access thousands of machines in order to do that? And again, every cloud was providing this as a fundamental service, but using a fundamentally different APIs. TESS was kind of a consolidation of what are the common elements that can be implemented on each one of these standards. So ideally, TESS is a common standard that is then implemented on the underlying interface under the hood. Can we go to the next slide? So again, from the researcher's perspective, you need to be able to execute tasks. You'll either use a common workflow engine like SnakeMake, NextFlow, Cromwell, CWL, or you could actually write a Python code that just sends out 1,000 jobs. And those are all available via the different libraries or workflow engines that are kind of speak this language. And then using this common API, they go talk to a GA4GH compliant system. Again, ideally, this system is just almost a wrapper layer or a thin shim up on top of a more, a kind of system-specific, infrastructure-specific implementation. So one of our collaborators right now is Microsoft, and they are implementing this standard, and it basically just turns around and directly accesses Azure Batch. And so they have a way so that you can take a GA4GH compliant workflow engine and just push it into Azure and not have to do any adjustments. And in fact, their motivation was they had to port the Cromwell engine that had been previously working on Google Cloud and make it work on the Azure platform. And their choices were either A, write a new driver and submit a bunch of pull requests into Cromwell and get that all up and running, or use the existing TESS API endpoint that had already been implemented in Cromwell and just use that as a way to then talk to a GA4GH compliant system and move it into a new infrastructure. And that's really what this is about, is enabling people to move quickly from infrastructure to infrastructure, almost at this cloud bursty style compute where you can write a management system that sends jobs to your HPC, but then easily turn around and point it at the cloud and be able to schedule thousands of jobs using the exact same management system. Can we go to the next slide? So just again, kind of emphasize how this is designed to be a kind of minimal, usable element. This is just an example of a request packet that you would see in TESS. And it is basically a bunch of input-output definitions. What files need to get moved into place? Where do they mount it inside the container? And then once the job is done, which files need to be pulled out and moved back into an object storage? You obviously have resource definitions. So you obviously, how much RAM do I need? How many cores do I want? How much disk space do I need? These are, of course, translated into cloud requirements, or if you're in a Slurm cluster, queue requirements. And then finally, what are the different command lines that are going to be executed, and what containers are they based on? So this means that every command line that you run, you can actually have an array of them that go one after the other. What command lines get executed in this environment? And then again, at the end of the job, what files are then packaged back out? And so this is just one packet, and this is kind of the TESS atom. Every job that gets sent out, or task basically that gets sent out in TESS, is one of these packets. And so they're pretty introspectable and you can move them around. Can we go to the next slide? And so again, thinking about that, once you're able to craft one of these packets and use that as a way to communicate your required workspaces, these are the different servers that will actually speak that language. And you just post these job packets to these systems, and they'll take care of the rest for you. My team has currently been working on one called Funnel, which is specializes in the HPC environment, but includes wrappers into AWS Batch. Most recently, been kind of debugging our Kubernetes deployment. There is an instance that was actually a module within Pulsar, which is a Galaxy kind of work distribution system, and so they claim to have be able to provide Pulsar support for test packets. Again, one of our major collaborators right now is Microsoft, and they're working on getting tests up and running in Azure. And finally, Elixir also has another implementation that's designed to support Kubernetes deployment. And then going back to that idea of these packets being introspectable, one of the servers we have is a proxy system that takes the packet and inspects it to figure out where it should distribute it to in a larger network. So there's this this basically a proxy system to, like, if you had like 7 different clusters, and it inspects the packet and says, oh, this job can be run at this institution, or this job, or maybe I should move it out to the cloud. And so that's what this proxy system basically sits on top of multiple test endpoints and then pushes them to the correct locations. Can I get the next slide? In terms of the client side of this, again, we have support in Cromwell. We have a CWL runner. I will admit that we probably could do a bit better on that one, but we're working on it. Nextflow support is actually a very recent full level. Previously, it was a beta, but actually, and I think the past couple of months, it's been released into production, and we consider it to be like almost a full support for Nextflow systems. There's PyTest, which is a library that lets you just do these commands yourself. So if you just want to say, again, generate 1,000 permutations of a command line and send them out onto the cloud and have 1,000 computers work on them, this is the library that would basically connect you to the servers. Again, SnakeMake, also something that's under still kind of under development, and we've also had some support in from Toil. Can we go to the next slide? The other thing I want to brag about right now is that we actually did get a paper about this API accepted into a special issue of kind of a hybrid computing cloud and HPC environments special issue for IEEE Computing Science Engineering. It's preprint right now, but that should be published in the next couple of months. So we'll have that to point at for the specification. And then can I get the next slide? So right now, I think, again, why are we talking here at at this Gen 3 meeting is what are the gaps, and maybe if you're more positive, what are the opportunities for this process? And so one of the things that we see right now is that the authentication, and this got mentioned in terms of like, the RAS and the passports and the DERS conversation, but how do you pass around authentication? And how is any authentication element connected back to an individual? Gen 3, obviously, in their IndexD system is tracking all of, which projects are available, which files are attached to which projects, which users can attach these projects. So using something like connecting like a test server to Gen 3 to manage that conversation, say, okay, here is these tokens that have been passed. Who actually can I talk to actually, figure out each one of these elements? That's an opportunity to connect one of these test servers to Gen 3 and use its infrastructure to manage the whole entire security conversation. Because one of the elements that is also on is like that necessary is how do things like S3 credentials get stored? Because not only like right now, like DERS is primarily a read-only API. So you go and find elements that exist, but test is actually generating novel elements. So when these new elements are generated, where can I write them to? And who has those credentials? And so we think that is kind of something that's important to get it a bit better. Again, Tesk and Funnel are kind of using these kind of global configurations. So basically one set of S3 credentials are loaded in for the server and you kind of use it in a kind of a small lab-like environment. We want to move to this more enterprise level version where you could service, an entire institution with a test server, and that all of the files and the subsequent output rights would be kind of mapped correctly to all of the different buckets. And finally, there's actually an opportunity here, again, in terms of provenance, because every command line that is run through tests has one of these test packets attached to it, which includes the logging information. It is possible to actually use, and it also includes the inputs and outputs. They're they could be DIRS IDs or S3 URLs, but you can go through each one of these, introspect them, and actually render back out an entire provenance graph of all of the different command line steps that were done in order to create a file. And this isn't, again, at a workflow level where you say, I took this file, I ran it through this giant workflow that did 40 steps and this thing popped out. You have every command line and every intermediate file recorded in the database. So you can see the entire process by which files traversed all the way through a workflow. And that could be, in the really cool scenario, loaded automatically into a Gen3 project. So anytime anybody does analysis on a file and creates a subsequent output file, you could theoretically load that into Gen3, and that would be already recorded in the project with the item registered for other people in the group to access. So those are the things we're thinking about when we think about how can we connect tests to Gen3 in a more substantial way that provides what we consider to be enterprise level support. And so those are kind of my thoughts for tests.
Great, thank you, Kyle. That's yeah, interesting to hear your thoughts on how to I guess the benefits of connecting tests and Gen3 and what the opportunities are there. So that's the content for the presentation, but I think I'd like to turn it over to the audience, the steering committee, the speakers to ask questions. I have a small question that I'll kick it off with. For I think Michael Lukowski. I was just curious about the gap between the metadata service and Data Connect. I know that you've said that they're kind of close. I'm just curious where they diverge.
Yeah, so the main place where they diverge is the metadata service has no concept of a schema. When you add data to the metadata service, all you put in is just a JSON blob. So the Data Connect service, Data Connect standard has the table concept, so that every single object inside of the Data Connect has its own table, or multiple things can be in the same table if they share the same schema. So the disconnect is that we have to add these tables to the metadata service.
Okay, that makes sense.
And along with that, I mean, the way it will actually work is when you add a data to, or when you add an object to metadata service, it will just parse the JSON, figure out what the schema is, and make the table be that. So it's sort of straightforward to how it's engineered, but implementation is tricky.
Any other questions? I just got my Zoom into drawing mode and can't get out, so I can't turn my video on until I figure out how to get out of drawing mode. But a number of us are down here at GA4GH, so if you haven't said hello, please say hello. Any particular requests for a future Gen3 community forum? Please send it to Michael Fitzsimons.
Hey, last chance for questions either in the chat or feel free to unmute if you like. Otherwise, feel free to follow up in the Slack community channel or you can email me directly. So thanks to the speakers and everybody for participating. Enjoy the plenary if you're there. Take care, everyone.
Thank you.
Thank you.
You.
Bye.